Okay, so what I want to do now is I want to look at this playful graph here and use the graph to find the local and global extrema using our definitions. And then we're going to come along and use this Desmos animation and try to figure out around local or global maxes, what can we say about the derivative? Okay, so right here, I see a little hill. This y value, f of minus 2 is 1.5. That y value is a local max. I'm going to just do local. I guess we have to do a local max. Similarly, right here, we've got, it's a different shaped hill. This is more like a mountain than like a hill, but it's still a local max. But the biggest y value, f of 5, is 4.375. This is my absolute or my global max. For local mins, I see right here I got a little bit of a hill. That's a local minimum. Similarly, right here, I've got a bit of a valley, but it's a steep cavern. It's a different shape, but we still have a local min. Now that local min also happens to be the absolute or the global min. That's the smallest y value, period. Okay, so now let's go look at that Desmos animation and see what we can about the derivative. Okay, so I am going to just slide this x value along. We've got a function that is continuous on its domain, and its domain is minus 2.75 all the way up to x is 5. So it's going to have absolute maxes and mins. It also has some local ones. Let's see. So right here where we had a local max, the derivative right there, f prime of minus 2 is 0. We got a horizontal tangent. Similarly, right here, when x is 0, the derivative at 0 is also 0 here because I have a horizontal tangent. The slope of a horizontal line is 0. And that's a place where we had a local min. And then right here, because of this sharp corner, that cusp, the derivative doesn't exist right here at 1, right? When x is 1, f prime is undefined. But we had a local max, and same thing right here, boop, boop. The derivative didn't exist at x equals, if I can get on it, if x equals 2.5, the derivative doesn't exist there, but we do have a local minimum. And then one more interesting thing, right here, bloop, when x is 3.5, the slope of the tangent line to the function is 0, the derivative is 0 there, but we did not have an absolute or local extrema. This function happens to be increasing on this entire part of the domain, subset of the domain. There's no hill, there's no valley right there, right? So, some observations. When we're in this open interval, right, going from minus 2.75 up to 5, that's 5. In the open interval is where we can have local or absolute extrema. The absolute extrema are the only ones that can occur at the endpoints, right? So in the open interval, what do we mean by that? Minus 2.75 is less than x, which is less than 5. You know, what observations do we have? we can have local or global extrema. If we do, what do you know? The derivative, how about is either 0, like right here, the derivative is 0, or right here, the derivative is 0. But just because it is, the derivative is 0 right there, but we don't have a local or an absolute max or min. If we do have a local or a global extrema in the interval, in addition, the derivative could be 0, but another thing that could happen is the derivative is undefined right there on these cusps, corners. On the endpoints, so what do we mean? X is minus 2.75 or X is 5. We can only have a global extrema there. And the derivative doesn't exist at the endpoint. But what we'll see here, we're laying the foundations for locating absolute extrema using the closed interval method. You're not going to have to, I'm sorry, I'm getting a little bit ahead of myself. I'm going to stop right there. So what did we learn? We learned that in the interval, we could have local or global extrema. If we do have them, the derivative's either going to be 0 or it's going to be undefined. But just because it's 0 or undefined doesn't necessarily mean you have a local or a global extrema. At the endpoints, you might not have a global extrema, like at this endpoint when x is minus 2.75, this y value of minus 7.97, that's not an absolute min or max, right? So they don't have to be one, but they could. Like here, we've got an absolute max occurring when x is 5. Okay? So Fermat's theorem. Fermat's theorem says that if these two statements are true, if a function has a max or a min, it's not specifying global or local, doesn't matter. Could be local. We don't even need to write that. Just has an absolute max or min at a particular x value, x equals c, and the derivative exists there, then what must be true? The derivative must be 0. Now, note, just because the derivative is 0 doesn't mean you're guaranteed to have an extreme value. If we look right here, when x is 3.5, the derivative was 0, f prime of 3.5 is 0, but this y value of 1 is not a extreme value at all. So f prime of, it was 3.5, yeah. Okay, so now these places where we could, places in the domain where we could have maxes or mins are called critical points or critical values, or sometimes they're called critical numbers. They're places where the derivative is 0 or undefined. So here's our definition. A critical point of a function is a number in the domain. It's an x value. Oh, I even wrote that. In the domain, such that either the derivative is 0 there or the derivative is undefined there. And again, we care about these critical points because they're places where we could have an extreme function value, an extreme value, but not necessarily. So notice in this little picture, we've got a horizontal tangent line, the derivative is 0, and it is in fact a local max. Here we've got a cusp, we got a corner, the derivative's not defined at x equals c, and we also have a local max. Same deal here. We got that sharp corner, the derivative's not defined, happens to be a local, we have a local min at x equals c. Right here, the derivative is 0, but this function it's always increasing. This function does not have any extreme values there at all. This is a lot like this part of this picture. And right here, my derivative doesn't exist because I've got a vertical tangent. The slope of a vertical line is undefined. And we also don't have any extreme values. So these are places where we could have some extreme values, but not guaranteed. All right, so now we've laid all of the foundation for us to go ahead and use our closed interval method, which we'll do in our last video.